In section 5.5, we're going to continue talking about triple integrals, but now we're going to look at how can we set up these triple integrals in both cylindrical and spherical coordinates. So I want to start by just reviewing. We'll do cylindrical coordinates first, and then we'll look at these integrals in spherical coordinates. So our cylindrical coordinates, I have the important equations up on the screen, was really an extension of that polar coordinates. So basically we use those polar coordinate definitions. X equals r cosine theta, y equals r sine theta, and then the only difference was because we're in 3 dimensions, we now have this extra z coordinate. So putting our triple integrals into cylindrical coordinates is going to be really similar to when we put those integrals, those double integrals, into polar coordinates. And so lots of math up on the screen. So what this is saying is if you have a triple integral, and if it's in rectangular coordinates, that dv is your dz, dy, dx. When you convert this into cylindrical coordinates, the dv, here it is, turns into an r, dz, dr, d theta. This is for the exact same reason we had that extra r in there when we put our double integrals into polar coordinates. So again, you're always going to replace the dv with the r, dz, dr, d theta. Now, I typically do the integration in this order, the dz first, then the dr, then the d theta, although you could do it in any order you want. Of course, the order you integrate in does impact those bounds of integration. If we're integrating with respect to z first, then our bounds of integration for z can have r's and thetas in them. And then we integrate with respect to r next. Those bounds can have thetas in them. And then finally, our thetas should be constants, if that's the last thing we're integrating with respect to. All right, and then of course we replace all the x's and the y's with r cosine theta and r sine theta respectively. So let's see how this works with an example. Let's see if we can convert the integral into cylindrical coordinates. So change this integral into cylindrical coordinates. So the very first thing I'm going to do is I'm going to try to draw a picture to describe what exactly is this volume that we're integrating with respect to. So again, the bounds of integration are describing the volume that we're integrating over. The z values are going from 0 to root 16 minus x squared minus y squared. And then the y values are next. That's going from 0 to root 4 minus x squared. And then finally our x's go from 0 to 2. So let's try to draw this. So first of all, the z values start at 0. That's just my xy plane. And they stop at this square root 16 minus x squared minus y squared. That equation is the top half of a sphere. If that's not obvious, you could square both sides. And then maybe it's a little bit easier to see that this is the top half of that x squared plus y squared plus z squared equals 16. So our z values are going from 0, which is our xy plane, up to that sphere with a radius of 4. All right, so that's our z values. And now the y values are starting at y equals 0. So y equals 0 is right there. And then they're going to square root of 4 minus x squared. Square root of 4 minus x squared, y equals square root of 4 minus x squared. If you square both sides, that's actually the top half of a circle with radius 2. So my y values are going from y equals 0 to the top half of this circle here. But then since the x's only go from 0 to 2, We are just in that first octant there, x equals 0 to x equals 2. So basically the object that we're integrating over, on the bottom, it kind of looks like this cylinder. I guess it's a chunk of this cylinder, we could say, in the first octant. And then the top of that object is this sphere with a radius of 4. And so that's the volume that we're integrating with respect to. So let's see if we can convert this into our cylindrical coordinates. So in cylindrical coordinates, let me circle what I'm talking about right here. This sphere with a radius of 4, this equation x squared plus y squared plus z squared equals 16, is the same thing as r squared plus z squared equals 16. That's just because the x squared plus y squared can be replaced with an r squared. So there's our equation of our sphere with a radius of 4. And then right here, I guess that cylinder, x squared plus y squared equals 4, is the same as r squared equals 4, or r equal 2. Okay, so I have the surfaces we're dealing with written in cylindrical coordinates to the right of my screen. And then to get this integral converted, I'm going to take the function we're integrating and put that in cylindrical coordinates. And square root of x squared plus y squared is just r. That's because the x squared plus y squared is r squared. You take the square root, it's just r. And then I'm going to replace my dv, that dz, dy, dx, with an r, dz, dr, d theta. All right, so I replaced the integrand, the function that I'm integrating, that's just r, and then I replace the differentials, the dv with the r, dz, dr, d theta. And now let's see if we can get those bounds of integration. So we're going to do the z values first. So the top of this object is our sphere with radius 4. And the bottom of the object is the xy plane, or z equals 0. So my bounds of integration for the z are going to start at 0. And they're going to stop at this sphere, which if you solve for z, that r squared plus z squared equals 16 turns into z equals the square root of 16 minus r squared. All right, so those are our z values. And then we have to do the r values. And so to find our r and our theta values, I'm just going to kind of draw what is the projection of this object on the xy plane. What does this object look like on the xy plane? And then I'll get my r and theta from that. So the region we're integrating over on the xy plane is just this circle with a radius of 2. That's just in the first quadrant. So that means my r values, the radius values, go from 0 to 2. And the angles, the theta, starts at theta equals 0, and we stop at that 90-degree angle, or pi over 2. And so there's my, my integral written in cylindrical coordinates. I might, just to make it look a little bit nicer, change the r times r to an r squared. And that's it. That's my final answer for this one. They didn't ask us to actually integrate this, so I'm just going to leave my answer like that. Let's do another one. This time we'll actually solve our integral. Let's see if we can set up an integral to find the volume of the solid bounded by x squared plus y squared equals 2y, z equals the square root of x squared plus y squared, and z equals 0. So first thing I'm going to do, as always, is draw a picture. What is this solid that we're actually trying to find the volume of? So x squared plus y squared equals 2y is actually It's a circle in the xy plane. So in three-dimensional space, it would be a cylinder. To help me draw that, I put it into standard form. So I just moved the 2y over, and then I did some completing the square. Half of 2 is 1. 1 squared is 1. So I added 1 to both sides. And that let me factor the y squared minus 2y plus 1 as y minus 1 squared. So I used some completing the square to take that equation and put it in a more standard form, because now I can see we're talking about a circle that is centered at the point x equals 0, y equals 1, and has a radius of 1. And so that's what I've tried to draw here. So there's my circle. Let me go back. There's my circle. And then it's actually continuing forever in the z direction. So we have a cylinder. I guess we're bounded on the bottom by z equals 0. So at least I know that. And then we're also bounded by this z equals the square root of x squared plus y squared. And if we square both sides, z squared equals x squared plus y squared, that's a cone. With that positive square root, we're just talking about the top half of that cone, centered at the origin. And so I've tried to draw that in purple on the screen. So the object we're talking about is basically this cylinder that has been sliced off on the top by this cone, which I've drawn in purple. So the top of this object is the cone. The bottom is z equals 0, and the sides come from this cylinder. That's basically what we're seeing. So I'm going to try to set up a triple integral in cylindrical coordinates to find the volume. And again, if I want to find volume, I just integrate 1. So I think before I get started, I'm just going to convert these equations into cylindrical coordinates. The x squared plus y squared is r squared. And then, so I'm dealing with this y in pink. The x squared plus y squared is r squared. And then I replace the y with r sine theta. And so that's how I got r squared equals 2r sine theta. Divide both sides by r. So r equals 2 sine theta. And then the cone turns into z equals r, just because x squared plus y squared is r squared. So z equals r. All right, so now I'm going to set up my integral. I'm just integrating 1 dv, which in cylindrical coordinates is the r, dz, dr, d theta. I'm going to start by putting in my bounds of integration for the z values, the heights of this object. The bottom of this object is z equals 0, the xy plane. The top of this object is the cone, what I've drawn in purple. And the equation of that cone is z equals r. So top is the cone, which is z equals r. Bottom, z equals 0. And then to get the dr and the d theta, I'm going to think about what is the projection of this object in the xy plane. And so let's see, this object in the xy plane just looks like a circle. I've since erased it, but that is supposed to be the same circle I had drawn in my three-dimensional coordinate system. So it's centered at 0, 1 and has a radius of 1. This circle has the equation, there it is in pink, r equal 2 sine theta. So my r values go from 0 to 2 sine theta. The theta values, in pen, so if you think about, again, we're thinking about when we put things in polar or cylindrical coordinates, we're thinking about slicing it up with these rays. And so I would say that theta starts at 0, and we're done with the circle once we get to pi. Theta equals pi. Okay, so again, my r's go from 0 to 2 sine theta. My thetas go from 0 to pi. Now, in this problem, they actually wanted us to find this integral, so I'm going to go ahead and do that. I'm going to start with my inside integral. So I'm integrating r dz from 0 to r. So antiderivative is rz. Plug in the r, plug in the 0, and subtract them. And that inside integral just becomes an r squared. And so now the second integral we have to do is the dr. So I'm going to integrate my answer, which was r squared, with respect to r. That gave me 1/3 r cubed. And then I'll plug in my bounds of integration and subtract. And I ended up getting 8 sine cubed divided by 3, or 8/3 sine cubed minus 0. So finally, to finish, I'm going to have to integrate. Let's see, I moved it over so I had more room. This is what I'm doing. I'm going to integrate the 8/3 sine cubed from 0 to pi. Let's see, I've got a sine raised to an odd power. Sine raised to an odd power. So I'm going to rewrite the sine cubed as sine theta times sine squared. Because then I can replace the sine squared with a 1 minus cosine squared. And this is now something that can be solved with a u sub. So again, I have an odd exponent, sine to the third. So I write that as sine to the 1 times sine squared. I use my Pythagorean identity on the sine squared. And the reason this works is now we can let u equal cosine theta. Our du is negative sine theta. And that actually allows us to rewrite the integral in terms of u. So my integral is now 8/3. Let's see, the sine theta d theta becomes a negative du. And then 1 minus u squared. I just took that negative with the du and distributed it to the 1 minus u squared. Wrote that as u squared minus 1. So integrate 8/3 u to the third over 3 minus u. U is cosine. So 8/3 cosine to the third over 3 minus cosine theta. And then finally, we're going to plug in those bounds of integration. So I'm going to plug in pi for theta, and then I'll plug in 0, and I'll subtract them. Cosine of pi is -1, and cosine of 0 is 1. So use those facts. Did a bunch of arithmetic. Hopefully I didn't make any mistakes. And my final answer was 32/9. And again, that answer represents the volume of this object. All right, let's do one more. Let's see if we can evaluate the following integral over the region described. X squared plus y squared less than or equal to 4. X is bigger than or equal to 0. X is less than or equal to y. And z is between 0 and 3. And so once again, I'm going to draw a picture, see if I can visualize what kind of region are we integrating over. X squared minus y squared is less than or equal to 4. So that's talking about everything inside this cylinder. X squared plus y squared equals 4 is a cylinder with a radius of 2. And so we're talking about everything inside that cylinder. And then x is less than or equal to y. Well, x equals y is a plane. If you draw the line y equals x, that's what I did in purple. So you just draw the line y equals x, and then that plane continues forever in the z direction. Now, if it's saying x is less than or equal to y, which portion are we talking about? Let me just draw this in 2 dimensions to try to explain. So there's y equals x. Again, we're saying x is less than or equal to y. That's the inequality we're thinking about. And so to know which side of this line are we actually referring to with this inequality, the easiest way to do that is to just pick a test point, just pick a random point that's not on that line. So for example, if I pick this point right here, let's say the point 2, 0. If I plug that into my inequality, 2 less than or equal to 0, that is a false statement. So what that's telling me is the inequality is everything on the other side of this line, everything above that line. And so back to my three-dimensional object, I drew my plane. So I have this plane that's slicing my cylinder, and the region where x is less than or equal to y, I've tried to color that in by drawing that kind of yellow object. So the part where x is less than or equal to y, we're talking about this kind of portion, this side of the plane. But we're looking at things inside that cylinder. And then let's see, I tried to draw it from z equals 0 to z equals 3. So our object starts at z equals 0, stops at z equals 3. So the shape I'm dealing with is what I've tried to draw in yellow. All right, so now let's convert our integral. The x squared plus y squared turns into the r squared. And the dv is the r dz dr d theta. Bounds of integration are z values. The height of this object is going from z equals 0, stopping at z equals 3, from 0 to 3. So those are my bounds for my z. And then I'm going to go to my r. I'm actually going to redraw this object, or its projection, I should say, in the xy plane to help me figure out my dr and my d theta. And so again, if we look at this from the top down, if we just look at the xy plane, we've got this line y equals x, intersecting our circle, x squared plus y squared equals 4. That inequality, x is less than or equal to y, is talking about above the line. It does also say x is bigger than or equal to 0, and so that's why I just kind of drew this little, looks like a piece of pizza in quadrant 1. Okay, so that's the region that we're thinking about in the xy plane. So based on my picture, I can see that my r values, I didn't write it out, here it is. My r values go from 0 to 2. So we're inside that circle, 0 to 2. And then the line y equals x slices this object at a 45-degree angle. So our thetas go from that 45-degree angle, which is pi over 4, up to pi over 2. So that describes this shape in yellow. All right, so now that we've got the integral written, now we just have to solve it. So I might as well take the r squared times r. That's r cubed. We'll do our inside integral first. Integrate r cubed with respect to z. We get r cubed z. Plug in my bounds of integration and subtract. And so that turns into 3r cubed. And then I'm going to integrate 3r cubed from 0 to 2. So I get, with respect to r, I should say, 3r to the 4th over 4. Plug in my bounds of integration and subtract, and I ended up getting 12. And then finally, to finish, we'll integrate 12 with respect to theta. Plug in our bounds of integration and subtract. So I got 12 theta. So 12 times pi over 2 minus 12 times pi over 4. That simplified all the way down to 3 pi. And so that's my final answer. This integral turns into 3 pi. So in all of these examples I've done, converting the problem into cylindrical coordinates actually made the integration much easier than were we to stick with the problem in rectangular coordinates. So cylindrical coordinates works really well when you have cylinders, which my last couple examples did. But in some cases, it might make more sense to put something in spherical coordinates. And so we have that option as well. So on the screen right now, I have a very quick review of our spherical coordinates that we learned about in the past. So spherical coordinates have a rho value, which is a distance from the origin to the point. That's our rho. And if you want to relate, and it helps me to understand this, to relate the spherical to the cylindrical coordinates, the r right here from our polar and cylindrical coordinates is always rho sine phi. So that kind of fact, it helps me understand where some of these equations come from. Okay, so anyways, rho is our distance from the origin. Theta is the exact same angle from our polar coordinates. So it's an angle in the xy plane made from the positive x-axis. Phi is an angle made from the positive z-axis. And then on the screen, I've got all of our different relationships for spherical coordinates. Hopefully this matches with what you have in your notes from the past. So if we want to convert an integral into spherical coordinates, we're going to replace the x with rho sine phi cosine theta, the y with rho sine phi sine theta, and the z with rho cosine phi. That's just the definition of spherical coordinates. And then the dv is right here. The dv, it turns out, is going to turn into a rho squared sine phi d phi, or I said that wrong, rho squared sine phi d rho d phi d theta. So you're always going to have this extra rho squared sine phi term in that dv portion of the integral. You can explain where that comes from using ideas from geometry. I think for just the sake of time in this video, I'm not going to do that, but I'm happy to explain it before, after, or during class if that's interesting to you. Instead, let's just see if we can convert the following integral. And in fact, this is the same problem we did at the beginning of this video. We converted this into cylindrical coordinates at the beginning of the video. So now, how are we going to put this into spherical coordinates? So same picture. So I kind of quickly redrew my picture just because I know it's the same as before. So we've got, we're just in the first octant, and we've got this cylinder, radius 2, and then the top of it is this sphere, comes from the sphere with the radius of 4. And so that came from these bounds of integration. Again, I did that really quickly just because it was the same problem I did earlier, so I just remembered what the picture looks like. The other thing I'm going to do right away, what I always do when I'm putting something into spherical coordinates, is I'm going to take my dz, dy, dx, and I'm going to change it to a rho squared sine phi d rho d phi d theta. All right, so now there's a couple other things we have to do to finish converting this integral. We have to convert the function into spherical coordinates, and then we have to figure out those bounds of integration. What are the rho values, the phi, and the theta? So I'll start by working with the function. Square root of x squared plus y squared. That's the same thing as r. It's the same thing as r from our polar or cylindrical coordinates. And r is rho sine phi. So I can convert that function into a rho sine phi. If that doesn't make sense to you, or you're not convinced of that fact, you could replace the x with rho sine phi cosine theta. You could replace the y with rho sine phi sine theta. Do lots of simplification, and it should simplify all the way down to rho sine phi. So I'm putting rho sine phi into my integral. I guess that makes it rho to the third sine squared phi, and then my d rho, d phi, d theta. All right, now for the hard part, perhaps. We got to figure out these bounds of integration. And so I kind of did some erasing. I redrew my picture so I had a little more room, fewer lines. So again, I have this cylinder, and then it's capped by part of this sphere. And so if we start by thinking about the rows, and again, rho is a distance from the origin. That distance is obtained by either the cylinder or the sphere, depending on where you are in that object. Okay, so again, if you think about drawing rays that come from the origin to the outside of this object, for part of this object, those rays land on the cylinder, and then eventually they land on the sphere. So what does that mean? That actually means, unfortunately, we're going to have to write two integrals. So we're going to have to break this up into two integrals because sometimes the rho, that distance, comes from the cylinder and sometimes it comes from the sphere. So before we do that, it's going to be helpful to know, where does this cylinder and that sphere intersect? Where do they cross? And so I'm going to use substitution with those equations to figure out where they intersect. So my sphere, x squared plus y squared plus z squared equals 16. Cylinder is just x squared plus y squared equals 4. And so then I took this x squared plus y squared in the sphere, and I just replaced it with 4. So the equations, the surfaces intersect when 4 plus z squared equals 16, z squared equals 12, or z equals root 12. So that intersection right there occurs when z is square root of 12. So anytime z is below square root of 12, it's like those lines I've drawn in blue. And the rho value, that distance, comes from our cylinder. And anytime the z value is above that square root of 12, it's like what I've drawn in red, that distance rho comes from the sphere. So we're going to set up two separate integrals to describe those two regions. Still integrating the same thing, rho squared sine squared phi, d rho, d phi, d theta. It's just we have to separate the bounds of integration. So our sphere in spherical coordinates, x squared plus y squared plus z squared is 16, turns into rho squared equals 16 or rho equals 4. So the equation of that sphere in spherical coordinates is just rho equals 4. And then our cylinder in spherical coordinates, our cylinder was the equation r equals 2. But once again, I'm going to replace that r with rho sine phi. So I guess it would be the equation rho equals 2 divided by sine phi, or rho equals 2 cosecant phi. All right, so those are the equations of our sphere and our cylinder. So the region I shaded in yellow, that portion, the rho values go from 0 to 4. Because that distance is landing on the sphere, so 0 to 4. The part I've shaded in green, our rho values are in the cylinder, so they go from 0 to 2 cosecant phi. Now we have to figure out the phi values, the angles that are associated with each of those regions. So what are the angles for the yellow and what are the angles for the green? And so I just kind of redrew that little yellow triangle to the side because this angle from the z-axis here, that's angle phi. So I just kind of put it in a triangle so I could try to figure out what that angle was. I know that these objects intersect when the height is root 12. And I know the radius of that cylinder is 2. And so I was able to draw that little triangle, which is, let me try to put it on my object. So this is the triangle I've drawn here. This little triangle here. Radius is 2, so this distance on the top is 2. Height of that triangle is root 12. So I can just use right triangle trigonometry to figure out what phi is. I ended up doing tangent is opposite over adjacent. So tangent is 1 over root 3, and that means that angle is pi over 6. All right, so this angle phi in this yellow region is pi over 6. So that means for the yellow portion, the angles go from 0, so 0 is just our positive z-axis, down to where they intersect, which is pi over 6. The part in green, the angles start at where they intersect. Phi is pi over 6, so the phi starts at pi over 6. And then we go all the way down to z equals 0, to our xy plane. And so that puts me, again, from that positive z-axis, that's what that angle is. From that positive z-axis, that's 90 degrees. So 0, or pi over 6 to pi over 2. So the green region has angles pi over 6 to pi over 2. And then finally, what is theta? Theta is the same angle in polar and cylindrical coordinates. So we're talking about this angle here in the xy plane. And that angle is from 0 to pi over 2, because we're just in that first octant. So those two integrals together can be used to evaluate that integral that was given in rectangular coordinates. And so this is an example where I think the cylindrical coordinates was easier than spherical coordinates. But there are going to be cases where spherical coordinates is easier, and usually that's when we have spheres. And in fact, let's do a triple integral to show what the volume of the sphere x squared plus y squared plus z squared equals a squared is. And since we're just working with a sphere, spherical coordinates is what makes the most sense in this problem. So if I want to find volume, my dv is always going to be, when you're in spherical coordinates, the dv is always rho squared sine phi d rho, d phi, d theta. So if I'm finding volume, I'm just integrating 1 dv, and so I just put the dv in spherical coordinates into my integral. So then what are my bounds of integration? The rho values, distance from the origin, start at 0, and always stop at a, because this is a sphere with a radius of a. The phi values, if we're talking about an entire sphere, so we start at the positive z-axis. To get the entire sphere, I have to go all the way down to the negative z-axis. So my phi values are 0 to pi. And then my theta values are 0 to 2 pi. So then I'm going to sweep that all the way around to get the sphere. So theta is 0 to 2 pi. Based on how spherical coordinates are defined, the phi values are never going to go above pi. I don't know if that's something that's throwing anybody off. Phi will always be at most between 0 and pi. You don't want to go past the negative z-axis and back up around, because the idea is to create the sphere, you go down to the negative z-axis and you've got this, I guess it looks like a half circle, but then when you rotate that around, that's what gives you the full sphere. So there's my integral, and now I'm just going to go ahead and evaluate this one piece at a time. So I'll start by integrating with respect to rho. So I get 1/3 rho cubed sine phi. Plug in my bounds of integration. So 1/3 a cubed sine phi. And then I'm going to integrate that expression with respect to phi. So now that gives me negative 1/3 a cubed cosine phi. Plug in my bounds of integration of 0 and pi. Let's see, cosine pi is -1, cosine 0 is 1. Do some math. That became 2/3 a to the third. And then finally, I'm going to integrate my 2/3 a to the third with respect to theta. Plug in my bounds of integration and subtract, and I end up getting 2/3 a to the third times 2 pi, or 4 pi a to the third over 3. And that is indeed the volume of that sphere. Right, that was my last example in this video. Please let me know if anything is unclear.